Our next application of integration comes from physics, where we talk about work. So in general, when we talk about work, just in the day-to-day, we're trying to think about the amount of work you have to do, like the total amount of effort that's required to perform a task. Well, in physics, of course, it's the same thing, but what does effort really mean? It means the amount of force, right? So if I'm thinking about moving an object, and in this particular application, this particular case, we're going to be moving an object one-dimensionally, right? Like along a line. So if I'm moving an object from point A to point B, a distance of say x, then the total, and I'm using a force that is just a constant force. So say I'm picking a book up off the table or something like that, where the force that I'm moving, I have to push against the force of gravity, and that's a constant. So then all I have to do to work is the force times the distance. Okay? So, and in general, that's going to be true. Now, if you've had physics and you know perhaps a little about vectors, then you might have seen that in some cases this is more complicated. I put a dot here for my multiplication because with vectors it is a dot product. We do that in Calc 3, so you don't at all have to worry about that. Here we're just doing motion in a straight line. There's nothing fancy, okay? So that's the idea. If the force is constant, your work is just the amount of distance that you need to be applying that force. But what happens if you have a force that's not constant? Okay, so that becomes a question. So a great example of this is a spring. Okay, I found a spring, right? Okay, so I found the little cocktail doohickey, but the spring comes off. And I think you guys can see that, like you can see that this is a spring, right? All right, that's as good as I'm going to be able to do on the internet here. But the thing about the spring is that when you're at the very edge of the spring, it's pretty easy to push it in. But the more you push closer, even my fingers are now stuck, the more you push in closer, the harder you need to press to get that compression. So the force that's required depends on how compressed the spring is, right? And we'll talk about that more later. And but that gives you the idea. So first, let's get that into just think about a variable force, right? So we're thinking about a variable force here. That depends on the distance. In other words, now my force is a function of x. It is dependent on the distance traveled. So what am I really doing with this? Let's see. So instead of A to B, let's look at this. Let us say that I have f of x at any particular point. So let's look at a small increment in x, right? So whatever that is, not the whole interval, just like a little one. Of course, delta x, right? So here's the point xi star, all right? So we are going to assume that this is so small that the force along my delta x is given by f of xi star, where xi is just some thing in that interval. Then, using this idea, we're going to do the work to move your particle from x to x plus delta x is again the force, which is f of xi star times the distance. And the distance is delta x, right? Because we moved it from wherever, x to x plus delta x. So that when I want to take this whole thing and make it, instead of just that little distance x, but the whole thing, right? So I've taken A to B, I've broken it up into little delta x's, but if I want to go all the way from A to B, I add them up, right? So I go I equals 1 to n of f of xi star delta x. And you all know what this is. This is a Riemann sum. If I take n to infinity, this becomes the definite integral. So I have a nice, simple, in this case, integral to do f of x delta x. So that's going to be the work. Now, then that's going to be work, meaning total work to move from x equals A to x equals B. Okay. So now just let me talk about this a little bit more. In terms of units, first of all, that's a good thing to mention, units, right? So these are going to pretty much be word problems. We'll be dealing with typically like a spring problem, or maybe there's a heavy cable that you're pulling up on the side of a building. A heavy cable rather than a book, like the idea being the book is the same, right? But if I've got like a heavy cable, then the weight of the cable itself is what I'm pulling up. So if I have the whole cable down, it's much harder to pull up than just a little bit at the end, right? So in that case, you're looking at a variable force that's required. So those are the kinds of problems we're going to be looking at. They are word problems. And because, of course, these are word problems, they will have units, and your answer has to have units. So your answer can't be 7, it should be 7 joules. All right, so let's just, and of course they involve distance, force, and work. Okay, so if I look at the units of force, okay, for metric, it's newtons, right? Newtons is basically the force, so it's actually F equals ma, right? So it's kilograms meters per second squared, but you don't need to know that. You can just call it N for newtons. Now if I'm doing work, you can see it's newtons times, okay, it's times distance. So here's the distance part, right? That's how it just looks like dx, but you don't want to forget the dx. That's the distance. That's going to also be in meter. So work, it's actually called joules, okay, and it's Newton meters, but you can also say Newton meters. If you write Newton meters, it's correct as well. I mean, if you forget that it's joules. Now, when it comes to English units, so English units, we've got pounds is a force. So if you remember pounds, although we think about pounds, as the weight of something, well, weight is actually a force, right? Because it includes gravity, all right? So your weight is a force. Remember the mass is slugs or something. I hate English units. But so weight is already force. And work then, force times distance, it's foot-pounds. Was it pounds foot or foot-pounds? Let's write this down. It's the other way. I said it right, I wrote it wrong. You see, I am not a fan of English units. Sorry. I don't remember how many ounces there are in a quart. But anyway, at least in this context, it's not that bad because it's just pounds and foot-pounds. You don't have to remember anything too awful. Okay, but I typically prefer the ones in metric, right? Okay, so let's talk briefly about the spring, and then in another video, I'll do a spring problem. do we discuss what goes on with this spring? And I realized that this was kind of floppy. It's a very floppy spring, right? And that's important too, right? So the floppiness of the spring or the stiffness of the spring actually has quite a bit to do with how easy or not easy it is to compress. So I thought maybe if I put it on the end of this spoon, at least it's not flopping all over the place. And you can get the idea. If you push it here, it's easier. If you push, it's already compressed some here. If you keep pushing it, it's harder and harder to push it, right? And whether it's talking about pushing it or pulling it, it's the same thing, right? It's a lot easier to pull it here than it is when I'm all the way out there. And though, in fact, though, it's just a linear relationship. It's just a proportionality. And that is Hooke's law, okay, which we can write down, we can say in words. In words, force is proportional to the distance from the natural length of the spring. So I'm going to write that down. Actually, maybe I should. Force is proportional. So what do I mean by the natural length? It's the unstretched length. And that's an important point because like these problems, the math is really easy, but it's easy to screw up and get the wrong answer because you set it up wrong. So this particular spring, its unstretched length looks about to be 6 inches. Okay, how about that's the wrong direction. Let's do it in centimeters. I got about 16.5 centimeters. All right, so that's the natural length of the spring. So it is where it is not undergoing any stretching or shrinking or compression. Okay. When I write this down, I write F equals Kx. This K is the spring constant, also known as the stiffness constant. So we often use K for stiffness, and basically the bigger K is, the harder it is to push the spring. So this one probably the K is not that big, right? So, but this X is not the length of the spring. The X is the length that the spring has been pushed. Okay, so if the spring is unstretched and I'm not doing anything, X is 0. If I compress it, X is the amount that I compressed it. So you have to be careful of that when you do the spring problems. That's all.